Hello students, so today I am coming with the new experiment, that is operational amplifier and its application, and this is your sixth experiment. So before starting to telling about the experiments, what we have to do in this experiment, right? So first we know what is the operational amplifier and what are the characteristics of the operational amplifier. After that we'll understand what we have to do and how we can use this application amplifier in various applications. Okay, so if you see the manual, here you will find study the inverting and non-inverting mode of the operational amplifier and its use for the different mathematical operation. That is our aim in this experiment. Okay, so the first thing is, what is the operational amplifier? It is basically high gain differential amplifier with two inputs and one output. And two inputs are, one is the inverting inputs and another one is the non-inverting inputs. Okay. So in this experiment we will use this one. This is the IC 741 LM741 IC. This is the commercial op-amp. Okay, so we will use this op-amp. Okay, so as I said, this is a high gain differential amplifier. So there will be some characteristics of this op-amp actually. So what are the characteristics of the op-amp? Like what is the input impedance, what is the gain of the amplifier, because I'm telling this is the amplifier. So what is the gain of the amplifier, right? What is the output impedance of the amplifier, and other things. Okay, so in the case of suppose if I'm designing the op-amp, which is ideal condition for the op-amp should be gain should be infinite, open loop, the maximum gain should be infinite for the ideal op-amp. Okay, and now come to the impedances. So input impedance should be a infinite and the output impedance should be a 0, and offset should be 0 also. Obviously offset should be 0 because there is a two inputs, and when both the inputs are the same potential or the inputs are same in both inputs, then output should be 0 because this is the differential amplifier. So you will get always the output a difference of gain times of difference of the amplifier. I mean whatever the gain of the amplifier into difference of the inputs. Okay, inverting and the non-inverting inputs. If the inputs are same, so output should be a 0. Okay, so offset should be 0. Okay, it should have 0 internal noise. Okay, infinite frequency bandwidth, whatever the frequency, this is another important thing. It should have infinite frequency bandwidth. I mean whatever the frequency of the input signals, gain should not be decreases. As you have seen in the previous experiment, that was a C amplifier where you got the finite bandwidth. But what we want actually in the case of operational amplifier, ideal operational amplifier, output should be independent of the frequency of input signal. That means infinite bandwidth. So there should be no gain roll off at the lower frequency and the upper frequency, means no cutoff frequency should come. So this is the ideal condition what we want, but practically obviously in the real op-amp we will have some finite value. Obviously there should not be infinite, so we will get some finite value. So as I show you this, we will use this 741 op-amp IC. So it will have some finite value, not infinite, like finite gain. It will have finite gain, finite bandwidth, but obviously it will be very large. not infinite, but it should be a large. So it has a 10 to power 2 into 10 to power 6 gain, voltage gain. Okay, this is actually voltage amplifier. Op-amp 741 is a voltage amplifier. So this, it has a 10 to power 6 gain. Suppose you are giving 1 microvolt, it will give you 1 volt gain as an output. When you give an input 1 microvolt, and you will get 1 volt at output. That much gain it can provide, mega, in order of mega. Okay, but it can it has a finite bandwidth also, not infinite, but bandwidth is very large. So at the lower frequency, gain will be very high, that is 10 to power 6. And as we increase the frequency, right, so gain will be roll off, gain will be decrease. That is if I say for the 741, it is minus 20 dB per decade. Decade means order of 10, right? So frequency will increase in decade, and the gain will decrease by minus 20 dB in each decade, order 100, 1000. Suppose if we now frequency is 100, so suppose gain is comes from 10 to 100 frequency. Now gain will come to 10 to power 6 to 10 to power 5. Now if we increase the frequency from 100 hertz to 1 kilohertz, so gain will come out 1 order per decade, right? So when gain will come out 10 to power 4, and so on. As we reach the frequency 1 megahertz, gain will become around unit 1. So it has finite bandwidth. We can operate this op-amp. We can give a frequency of input signal within the bandwidth, so that gain we can get the constant gain. Okay. So op-amp has 741 has 2 mega ohm input impedance, and the output impedance obviously it is low, so it is 75 ohm, around 75 ohm. Okay, and the current, maximum on current can be drawn for the 741 is 20 milliampere, and the recommended output should be greater than 2 kilo ohm. Okay, and the offset is ranging between 2 millivolt to 6 millivolt after nullify it. And one more thing I want to tell you, that is the slew rate. So what is the slew rate? One parameter is also defined. So slew rate is actually what is happening. You are applying the signal at the input, and it will have some frequency. I mean, input is changing with time, but op-amp should capable to respond that change and give at the output. So there should be no delay between input changing and the output changing. So that is why one parameter is defined, that is the slew rate, which tell us how much maximum change in input signal we can provide. I mean, how much frequency of the input signal we can give, so that output should not be distorted and op-amp can respond that fast or high input signal. Okay, so usually it is known as a volt per microsecond. For op-amp it is a 0.5 volt per microsecond. Okay, so these are the things. So in the case of practical op-amp, that is the real op-amp, so bandwidth is finite, gain is finite, but are very high. In ideal condition, it input impedance is very infinite, but we have very high, that is 2 mega ohm, and the output should be 0. Okay, but we have some finite, that is 75 ohm. So which is quite closer to, not closer, but we can use this op-amp as in place of ideal op-amp. Okay. So as I said, it has two inputs. One is the inverting input and another one is the non-inverting input. Because it is a differential amplifier, so obviously there should be a difference. Amplification should be difference of two inputs. So one will give you output as an inverted of the input. That is why it is called inverted input, inverting input. And another one is a non-inverting input, because if you give the input at the non-inverting, you will get the output is the non-inverted of the input. I mean, you will get the same phase output. Okay. So what first thing is, so as I said before doing the experiment, obviously we have a real op-amp. So first what we will do the offset we'll adjust the offset, because obviously because it is a real op amp, it will have some offset. So we have to nullify it by adjusting some bias voltage, DC bias voltage, so that without giving any input, we should get output 0, or if we give the same input at the input, output should be 0, because we are getting the difference of inputs, and to the amplification voltage gain. So if the input is same, output should be a 0. Okay, so we will just offset the op amp before starting the experiment. So let us start. I will tell you, if you see the manual, if you can see the manual, this is the IC diagram, this is the equivalent circuit diagram of the op amp. You can see here equivalent circuit. This is a non-inverting input, this is the inverting input, this is the bias voltage of the differential amplifier, you can say, which is VCC and VEE, or V plus 5 and minus 5. So one more thing I want to tell you. So to operate this IC, we need a minimum of 5 volt plus minus 5 volt to maximum plus minus 18 volt. So I will use plus minus 15 volt usually to get high gain, and so that it can perform well. So, and this is the output. Now I'll identify the pin configuration. If you see the op amp, so if you take here, this is the actual op amp, real op amp, and this is the pin diagram of the op amp. Okay, so if you see, there is the notch or circle, there is a dot, right here you can see. So this dot is represented as to identify the pin numbers. So obviously there is a dot, so near one is the near one pin is the 1 number, and if we start counting it from the anti-clockwise, so first one will be the 1, second one will be 2, third one will be 3, and fourth one will be the 4, pin number 4, and come to the above. So 5th, 6th, 7th, 8th. So in front of 1, 8 will be, in front of 2, 7 will be, and in front of 3 obviously 6, and in front of 4 there will be 5. So here you can see there is a pin number 1, 2, 3, 4, now 5, 6, 7 and 8. Now we'll identify what is the pin number 1, what is the pin number 2, what is the pin number 3, and so on. So pin number 1 is offset pin, pin number 2 is the inverting input, pin number 3 is the non-inverting input, pin number 4 is the minus V, that is VCC and VEE, as I said. So this is minus VE actually, so minus voltage we will provide here, and pin number 5 again is the offset, pin number 6 is the output. So here you can see the triangle diagram. This is the symbolic diagram of the op amp. We are representing by the triangular shape. So 2 is for the input and 1 is for the output, and the 7 one is the plus VCC, okay, or plus V voltage, and at 8 is the not connected. We'll not going to use this pin throughout the experiment. So there is the 2 pins for the offset. One is for the negative voltage, and 2 is the input, 1 is the output, 1 is the plus V. So if you see in detailed, so 2, 3 will be the input, 1, 5 and 4 will be used to offset the op amp, okay, and 7 and 4 will be the will provide the DC supply at the 4 and the 7, positive VCC and minus VCC, and we'll take output from the pin number 6. Okay, so I am going to connect this op amp IC on the breadboard. Here you can see. Okay, so IC is connected on the breadboard. Now what we have to do, we have to adjust the offset. So okay, so for that we need DC power supplies plus minus VCC and V minus VCC. So I will use multi-channel DC power supply, So this DC power supply will provide me plus 15 volt, minus 15 volt, and that will be the 0 volt. So this plus 15 volt I will connect at the pin number 7, because VCC plus VCC should be connected to the 7 number, pin number 7. So I will connect plus 15 volt VCC at the pin number 7. Okay, so 1 2 3 4 5 6 7. So this will be a 7 number. Here you can see this is the 7. Okay, and now I am going to connect minus 15 at pin number 4, because you can see minus VCC is connected at, here you can see that minus VCC is connected at pin number 4. Okay, so 1 2 3 4. So I am going to connect pin number 4 with minus VCC. So plus VCC are connected at pin number 7, minus VCC minus V voltage is connected to pin number 4. Okay, now this is the ground one. This is the ground. It should be connected at pin number. It should be connected at the pin number 5. So which one I can use? This one. Okay. Okay. Now I will connect this potentiometer, as you can see in the op-amp, manual. This 10K potentiometer is connected between 5, 1 and 4 to adjust the offset. So here is the pin number 5 for offset. Okay, offset net, and pin number 1 and pin number 5 both are for offset null, and 4 will be the common to the negative VCC. So this is the potentiometer. Actually this is a 5K we have. Okay, this is multi-turn potentiometer with high precision. Okay, so this will, I will connect this one at the pin number 1, pin number 1, and another one will connect at pin number 5, and the remaining one will connect at the pin number 4. Okay, so we will adjust this potentiometer to nullify the output DC voltage when it will give nothing at the output. I mean, we will just ground it, as you can see in the circuit diagram. We will just ground the pin number 2 and pin number 3. Okay, now I am going to connect pin number 2 and pin number 3 to the ground. So this is the pin number 2. I am going to ground it, and this is the pin number 3. Pin number 3, I see pin number 3. Again I am going to ground it. Okay, yes, so both are the ground. So this is so this is the ground. So I will connect this with pin number 2 and 3 by connecting here. Here you can see, so I am connecting this. Ground terminal is connected to pin number 2 and 3 directly. Both are connected at 2 and 3. So input is 0. We are not giving any input. Both are the grounded. At the pin number 1 and the pin number 5 and the pin number 4, this rheostat is connected, this potentiometer is connected. At pin number 7 and pin number 4, plus minus VC connected, plus is connected to pin number 7, minus 15 volt, that is minus VC is connected to pin number 4. Here as you can see the circuit diagram. According to this, we supplied the VCC at pin number 7, we supplied the minus VCC at 4 number, we connected potentiometer minus 1, 4 and 5, and we grounded both the inputs, that is inverting and non-inverting. This is the inverting 2 number, this is the non-inverting 3 number, and both are the grounded. As you can see, this is the, we are just connected this both connected with the ground. So at the output is left. Now I'll connect the output with the multimeter to see the output voltage, DC voltage, so that by adjusting the potentiometer we can minimize the output voltage. Okay, whatever the mismatching at the input, so we should be minimize it by adjusting the bias VCC plus minus VCC by adjusting this potentiometer. So now come to this digital multimeter. I will use it as a voltmeter. So I will use it as a voltmeter. Now I am going to connecting it plus, and so this positive terminal I am going to connect it at the pin number 6. Okay, so it is connected at pin number 6, and the negative one should be connected to the ground. It should be connected to the ground, and the pin number 8 is left, is not connected. Okay, so circuit is almost done. Here you can see these are the grounded 2 and 3, and from the multimeter it is grounded. Okay, now I can start the circuit. I can give the power supply to the multi-channel power supply and voltmeter. Okay. Okay, so right now VCC is plus VCC is 15 volt, minus VCC is almost 15.1, almost 15 volt. So we are getting plus minus 15 volt, that is 30 volt at pin number 7 to pin number 4. Right now we are getting voltage is 14.5 as an output. What is happening here? We are getting the maximum output. So when the right now op-amp is in a open loop, we are getting the very high gain. Okay, so that is why it is got saturated at the positive. If I adjust it, see the multimeter. Yes, see the multimeter. Just focus on the multimeter, please focus on the multimeter. If I adjust the potentiometer, here you can see right now it is 14.5 volt. I am moving it. See, suddenly it come to the 12.9 minus 12.9 volt. So it is saturating plus 14 to minus 13. So why it is happening actually? Because of the high gain at the input. Because we are op-amp is an open loop gain. We are getting the open loop gain. So how will adjust? How will do the offset null right now? So one thing I can do, we can reduce the gain of the open loop. We can reduce the gain of the amplifier. So how will do it? By applying the feedback, negative feedback. So I have two resistors for that. One is 10k ohm, is it focus on that, or yes, 10k ohm, brown, black, orange, and the another one is brown, black, red, that is 1k ohm. So I will connect this 10k ohm as a R2 in the feedback, and at the input I will connect 1 kilo ohm. Here you can see, if you see the circuit diagram, R2, this is the negative feedback because it is connected at the inverted input. So output is connected to the negative terminal of the input op amp, input of the op amp, that is the inverting point. So R2 upon R1. So this is the gain of the inverted op amp condition. So R2 by R1. So voltage gain should be R2 by R1. So right now I am choosing R2 as a 10 kilo ohm and R1 is as a 1 kilo ohm. So gain will be 10. So at the open loop gain, obviously it is very high, order of 10 to power 6. So I am reducing it at the 10. So now I am going to connect these two resistor. Okay. So first I will just turn off the power supply. So here you can see it is connected. Here you can see pin number 6 is connected through the resistor through the pin number 2, because 2 is the inverted input. Here you can see inverting input. So R2 is connected between pin number 6 to pin number 2, and R2 I have chosen, that is 10 kilo ohm. So I will connect this. Okay, so I am going to connect. Okay, so you can see pin number 6 and pin number 2, and it is connected between this 10k ohm is connected between pin number 6 and pin number 2, which is R2. Now I am going to connect this R1 resistance from R2 to, it should be a ground. So I will remove this grounded R2 resistance. So okay, then this is, now it is connected. Okay, and after R2, after R1 it should be ground. Now it is grounded. So R1 is grounded at the one terminal and another terminal is connected at to input of the inverting input, at the inverting input. So I am just corrected the feedback resistance so that its range should be decreased. Now it is 10 because R2 is 10 kilo ohm or R1 is the 1 kilo ohm. So now the gain is 1. So gain is 10. So now the output gain should be come like right now this is 12 volt. Okay, I'm adjusting it. So okay, so I'm just adjusting this potentiometer to make it, right now output is right now you can focus on this multimeter, and this is the okay. Now so I'll adjust this potentiometer in such a way so that the output should become 0, almost 0. Right now it is minus 0.3 volt. So I will adjust it in such a way. Right now 4.6 increasing, so I'm moving opposite direction. Yes, it is decreasing, start decreasing. Right now 2.18 minus 0.15, 14, 12. Okay, so right now it is minus 96 millivolt. Okay, so yes, it is still decreasing. Yes, minus 37 millivolt, minus 25, 22, 19, 16, 15, 14. Okay, minus 3 millivolt, minus 2. Okay, 0.1 plus 0.1, minus 3, minus 4. So now right now you can see it is 0.2 millivolt, which is very small actually. So we are closer to offset actually. Okay, so yes, here you can see it is fluctuating plus minus 0.1 millivolt. So I will not disturb this potentiometer throughout the experiments. Okay, in the entire experiment I will not touch this potentiometer, otherwise if I touch it, its offset null will be disturbed. Okay, so I will not touch it, and throughout the experiments, and will not remove this potentiometer from the circuit. Okay, so here you have seen this is the process for the nullify the input, that is the offset nullification process. Now the first part of the experiment is, first objective is see the inverting and the non-inverting amplifier. So the first objective is to construct inverting and non-inverting amplifier, and we'll see how it is performing, whether we are getting gain or not, and how much gain we are getting. Right now feedback is 10, so gain will be the 10. Okay, feedback we have connected the resistance in such a way so that the gain now become 10. So when we'll give the input, suppose it is a 1 volt, so output should be a 10 volt. So for that I will use this function generator for giving the input. So it has two separate channels, so we'll get two different inputs. So okay, and this is the DSO, so I will use this DSO to see the whatever the input we are giving in the op amp, and whatever the voltage, whatever the signal we are giving after the amplification from the op amp. Okay, so I'm going to on this DSO and the function generator. Okay, so this is the coaxial cable, BNC cable, and this is a crocodile to BNC cable. So this is connected to the function generator. Okay, so we will give the input, okay, to the op amp. Suppose now first we will see the inverting amplifier. I will see the inverting amplifier. So for that we will ground the non-inverting terminal, that is the ground, that is the 3 should be grounded, and 1 should be we will give the signal at the non-inverting term through the R1 resistance. Okay, so as you have seen during the offset process, we just grounded the inverting terminals, that is after the connecting the R1. So I will remove this wire. Okay, so this is the R1 and this is the another end. So I will give the input signal here. I will connect it. Okay, so this is the input and it should be grounded. So I will connect this at the ground. Okay, so we are giving the input of 4 volt 1 kilohertz, and we'll see the output at the, and we can see this input signal here, which is directly connected to the channel 1 of the DSO, and channel 2 we will use this channel 2 to see the output of the DSO, which is actually right now connected to the multimeter. So I will remove this. I am going to remove this multimeter. Now this is connected and come to the ground. So this is the ground part, and this is the ground here. Okay, so input signal, what I have done now, so input is connected to the R1 resistor, and which is grounded, and directly we can see the input from the channel 1 of the DSO, and output of the op-amp, which is connected from the pin number 6, and we are seeing this at the channel number 2 of the DSO. So I am going to make it auto scale so that we can see both the signals. Okay, as you can see, channel 2 is the output, which is green one, and the channel 1 is the input. We are getting some distorted signal because right now we are giving input signal which have 4 volt peak to peak, 1 kilohertz frequency, and 4 volt peak to peak. So output must be 40 volt, but we have connected DC power supply VCC to minus VCC, which is 30 maximum, plus minus 15, 30. So we cannot go beyond that. So right now what is happening, op-amp is saturating at plus 15 to minus 15. Okay, so I'm going to reduce the amplitude of the input signal. Right now it is 4 volt, so I'm going to fix it at 500 millivolt or 0.5 volt. See, right now it is 500 millivolt and frequency is 1 kilohertz. So again I am going to auto scale it. Okay, so we are getting nothing actually, right? So okay, yes, sorry, connection was little loose, that is why it is fluctuating. Okay, again, yes, now here you can see we are connected the input at the inverting terminal. That is why we are getting the inverted output of the input signal. Here you can see this is the input signal, and this is the green one is the output signal, yellow one is the input, and you can see easily there is a 180 phase difference. That is why we are calling it inverting input, because we are getting the inverted of the input signal. Okay, and if you see the amplitude, peak to peak amplitude, so this is the channel 1, this is one, yellow one. Now right now it is 510 millivolt peak to peak. This DSO can measure amplitude of the input signal is 510. However, we are giving the exactly 500 millivolt, but we are getting 510. There is a error, instrumental error, so we can assume it as a 500 millivolt. But here you can see at the output, peak to peak output, that is here it is written 2, because we are taking output from the op-amp at the channel 2 of the DSO, which is 5.1. Input is 510 millivolt, output is 5.1 volt. Obviously this is 10 times larger, and we have fixed the feedback resistance, that is R2 by R1, which was 10 kilo ohm by 1 kilo ohm, that was the 10. So feedback was fixed in such a way, so gain of the amplifier should be 10, and we are getting exactly the same. Input is 510 millivolt and output is 5 volt. Now come to again, if I change the input signal, right now 500 millivolt, I am going to increase it 600, right now 600 millivolt. Here you can see this is 630, it is fluctuating actually 610 to 620. Again you can see now voltage is 6.1. Again if I increase it 700 millivolt, this is 700 millivolt, I am getting 7.1 volt at the output. Okay, again I am going to increase at suppose I am going to fix it at 1 volt. Okay, here you can see 1.07 volt. Right now output is, it is fluctuating between 1.05 to 1.07, and the output is 10.5 and 10.7. Obviously exactly 10 times of gain we are getting at the output. So signal is getting amplified 10 times of the input. see here I am changing the amplitudes, and here if I change frequency 1, right now 2 kilohertz, 3, so gain is almost same because it is very small change in frequency. Okay, so this is the inverting. Now come to the non-inverting. We'll see the another one is the non-inverting input. So we will give the signal at the non-inverting. Okay, so before doing the non-inverting, I'll just save this display, I mean the signal input and output, to give you the data. This is for the data only, so I'm going to save it. So save to USB. Okay, so file is saved successfully. Now it is saved at the in the USB drive, that is a pen drive. Okay, so data is saved. So it is for just 1.1 volt at the input, and we are getting 11.5 at the output for 1 kilohertz frequency. Now if I change the input, right now we are giving the input at the inverting terminal. We will see what will happen if you give the signal at the non-inverting terminal. Here you can see. So inverting terminal I will ground it, and I will give the signal at the non-inverting terminal, that is the pin number 3. So pin number 2 will be grounded through the R1 resistor. Here you can see this is the input coaxial cable. Okay, so this is the input is connected right now. So I am going to remove it. Okay, here you can see output is removed. Output is now become 0. Okay, and pin number 3, here you can see pin number 3 is grounded. So I'll going to remove it, and I'll connect it as the input. Okay, as an input, and pin number 2 through the resistor I will ground it. Yes, so yes, connected. So here you can see this is the input from the function generator. This is I'm directly seeing from the function generator, and this is the output of the op amp. Now here you can see this is the non-inverted 0 phase difference. I am giving the input of the function generator at the non-inverting terminal of the op amp 741. Okay, and I am getting the same output with the 0 phase difference. That is why it is called non-inverting with the gain. Okay, now come to the gain. So the gain for the non-inverting configuration, it is defined as 1 plus R2 upon Rin. So right now the ratio of R2 upon R1 is Rin means R1 obviously. So R2 was 10 kilo ohm and R1 was 1 kilo ohm. So their ratio is 10. So output 1 plus 10 should be 11. If I give 1 volt at the input, the output should be 11 volt, not 10 volt. Okay, as it was in non-inverting. Okay, with minus sign, minus R2 by R1 V in, and here it is 1 plus R2 by R in, which is it will give you for this feedback we will get 11. Okay, 11. So here you can see right now the input is there is 1 volt peak to peak and 1 kilohertz frequency. So input is 1.1 peak to peak. Almost we are getting, actually we are giving 1 volt. So 1.1 and at the input, and we can see peak to peak of output voltage is 12.1. Why 12.1? Just multiply it 1.1 into 1 plus 10, that is 11. Okay, so you will get almost 12 volt. 11 plus 1, that is 12 volt. 1.1 is become 11 and plus 1, that is 12 volt. Again, if I change the input now, right now let us say 500 millivolt, that is 5.5 volt. So 500 millivolt gain should be 5 volt plus 1, it should be 6 volt. So input is, it is showing 600 millivolt, and I am getting 6.5. So not 600, there is some actually noise actually. So if I change it to 2 volt, suppose 2 volt peak to peak, now that will be okay. Right now 2.17 volt at the input, and we are getting 23.7, that is 21 plus 1, 21.7 plus 1. Okay, so almost we are getting like that with the non-inverting output. So these two was the first objective of the experiment. Okay, we just constructed the inverting and non-inverting amplifiers, and we have seen their performance. Now again I am going to save it to USB for the data purpose. Now it's saved. This again, this is also saved. Okay, so this is the first part of the first objective of the experiment. Second one, we will see the application of the amplifier op amp, like mathematical operation like addition, subtraction. Even we will design the integrator and the differentiator. Actually I have done some circuit connection already. So as you can see here, at the inverting terminal there is 2 resistance. This is showing for the unit gain, because feedback resistor is 10k and the input resistor also are 10k and 10k. So as you know, for the inverting and non-inverting I used R1 resistor is 1k, so still I am using 1k, but here you can see another input is given at the same inverting terminal by connecting the resistor with the same value of the R1. So here it is 10k, so I'll use in our actual circuit 1k and 1k, and here the sign signal will be signal 1 and signal 2. So in the case of inverting, it was already sign signal was connected. Now the one thing I will connect, that is the 10k resistance and one new sign signal by using the function generator, because my function generator have 2 separate outputs. Okay, so here I'll connect this 1k and 1k. Okay, so in the breadboard here I have already connected this. So here you can see, so previously I was connected this 1k ohm as R1 at the inverting input, that is the pin number 2. Here again I have connected one more resistor with the same value, that is 1k, and this is connected to the, here you can see this is connected to the another input of the function generator, that is here you can see. So this is the channel 2 and this is the channel 1 and channel 2. So at the inverting input I have just connected these 2 signals through the 1 kilo ohm resistor, okay, this one and this one. Here you can see through the resistance 1 R1 and again R1 with the same value, R1 both are the 1 kilo ohms. Okay, and again so output is taken at the pin number 6. So here you can see, so we have 2 input signals at the inverting terminal through the resistance 1 kilo ohm resistance. So gain is still 10. Okay, so whatever the signal we will give at the inputs, obviously from the channel 1 and channel 2, so we will get the output signal, their sum of and multiply by the gain of the amplifier, which is 10. So right now here you can see, so what will I do, I will just take the one's input as a reference here at the channel 1. At the channel 1 you can see right now is 1.5 volt peak to peak and frequency is 1 kilohertz, and at the channel 2 it is a 0.5 volt, that is 500 millivolt, and same frequency. The both signals have the same frequency, mind it. Okay, so both the signals have the same frequency, but their amplitude will be changed, and we'll see how their amplitude will add up. So that is why I am calling it as a adder circuit. We can use also DC supply also, but if I give 1 volt and different from the one input, and another is 0.5, so their output will be 1.5 and multiplied by the gain. So similarly I am doing here also. So right now I am giving the 500 millivolt from the one channel, channel 2, which is connected to the inverted circuit through the 1K resistor. And again you can see at the channel 2 it is 1.5 volt. So we are giving 1.5 at the one input V1, and we'll take as a output of channel 2 as a reference. So we will not change output of the channel 2, okay, of the function generator. I mean, here I will fix the one voltage signal amplitude of the one signal, and I will vary the signal amplitude of the another signal. So I will see how the output is changing. So one is fixed, another one will vary. We will vary this another one signal, and we will see how output is varying. So that is the thing I will do here. So right now at channel 2 it is 0.5 volt or 500 millivolt, 1 kilohertz frequency, and now I am just going to change it 0.5 volt peak to peak. So input is both the input are 1 kilohertz frequency and 500 millivolt or 0.5 volt. Okay, that is the thing. So you can see here. So you can see this is the input signal, which is I am taking from the this is the input signal. Yellow one is the input and green one is the output. Here you can see, which is directly connected to the input of the channel 1 of the DSO. So here you can see at the okay. So here you can see, so peak to peak, that is 510 millivolt from the channel 1, and from the channel 2 you can see again 510 millivolt peak to peak. This is the input actually. So I will keep this channel 2 input is fixed. I will fix it, or I will treat it as a reference. Now I will going to change. So this is the fixed. So I will see the change in the channel 1. Channel 1. I will change the channel 1 signal, and we'll see how the output is changing. So right now it is 0.5 volt. So input is 0.5 volt. Both the input is 0.5 volt, 1 kilohertz frequency, and we are getting the output is, which is fluctuating 10.9 to 11.1. So this is 5.1. So 510 millivolt in each input. So that means it should be 510 millivolt. That is 1020 millivolt. So 1020 millivolts, that is 1.2 volt. This is actually we are giving 1.2 volt, and their output should be into 10 times, right? Because it is a inverting R2 by R1. Okay, so it should be, you can see here I am getting 10.2 instead of 11.9 or something. It is fluctuating 11.3 to 11.9, even 10.9 to 11.3, something like that. So this is the resultant output. Okay, here you can see we are getting some output, and the inverted output we are getting, and which is the sum of the two inputs from the channel 1 and the channel 2. Both are the same. Okay, so I am going to save it, okay, to the USB. Now the display is saved. Now come to the now again I am going to change it from the channel 1. I am going to fix it at 1 volt peak to peak. So let's see what will happen. So see, input of the channel 1 is changed. So I am going to reduce it. Yes. So right now peak to peak of the input is 1 volt, and from the channel 2 it is 0.5. It was fixed, right? So actually what we are giving 1.05 and plus 0.5 volt, that is 1.4 volt we are giving, and we are getting 15 volt. Correct? So gain is 10. From the channel 1 we are giving 1 volt, from the channel 2 we are giving 0.5 volt. So they are sum up, that means op-amp will sum up these two inputs, 1 volt plus 0.5 volt, and it will multiply by the gain, that is 10. So 1 plus 0.5, that is 1.5 into 10, and the so output is amplified with the inverted output is amplified by 10 times. Now it become 15 volt. So that is the thing, it is adding actually. Now again I am going to show you by changing the input of the channel 1. So right now it is 1 volt, so I am going to fix it at 1.5 volt peak to peak. Okay, so here you can see 1.53 of the channel 1, and obviously from the channel 2 it was 0.5 volt which was fixed, and I have considered it as a reference. So 1.5 plus 0.5, that is 2, I have multiplied by its gain 10, so it become 20 at the output. So both the signals are adding actually here, and by gain it is multiply, so we are getting the gain of the inputs. If gain is 1, so we will get, obviously we will get the 2 volt at the output right now. So again I am going to save it. Okay, so next circuit is subtractor circuit. So here you can see in the manual there is the 2 input V1 and V2. So I will take one is reference, and I will take another one, I will change the another signal, and we will see the how the difference is coming out at the output with the given gain of the amplifier. So in detail we can see the circuit here. So this is the circuit. Okay, I just drawn the very clearly. So previously in the adder subtracted I use R2 was 10 kilo ohm, R1 1 kilo ohm, and here R3 and R4 I also assumed I connected 1 kilo ohm and the 4 kilo ohm. So if you see the gain of this differential amplifier, so gain output of the amplifier will defined as a inverting gain plus the non-inverting gain. So this is an inverting gain because we are giving V1, it will give the gain inverting, and from the V2 we will get the because of this R3 and R4 resistors we will get non-inverting gain. So this is traditional feedback gain, 1 plus R2 over R1 negative. Okay, and this one is the voltage, how much voltage is dropping across R4 resistance. So this will be the gain. Here I assumed R1 equal to R3 and R2 equal to R2 equal to R4 for simplify this equation. Output gain, okay, output voltage. So now it will become V out equal to R2 over R1 V2 minus V1. So I just connected 1 kilo ohm, 10 kilo ohm, 1 kilo ohm and 10 kilo ohm. Okay, so the circuit here you can see this is the feedback. Okay, R2, R1, this is again R3 and R4, sorry, R3 and R4, and offset already done. So the circuit is actually connected. Now see, again you can see 15 volt plus minus 15 volt. Right now the input is given. At the channel 1, which will show you, which will get the V1 and V2. Okay, so I'll assume it as a V1 and V2. So right now at channel 1 we are giving 1 kilohertz frequency and the 500 millivolt in amplitude peak to peak. Okay, sine wave, and the channel 2 is right now it is 1 volt, 1 kilohertz frequency, same. So right now we are getting, this is yellow one is the directly we are seeing at we are observing the output of the channel 1 at the DSO channel 1, which is this yellow. So this is the input, okay, one input, and we are taking output of the two differences of the op amp. Right now input is from the channel 1 is 550 millivolt peak to peak we are getting, and we are getting output voltage 5.6. How we are getting? Because if you see, we are giving channel 2, that is V2. Right now V2 is 1 volt and V1 is from the channel 2, V1 is 0.5 volt. Okay, so 1 minus 0.5, it will give us 0.5, and as we know R2 is 10 kilo ohm and R1 is 1 kilo ohm. Okay, so this is the gain, resistance gains, feedback gain is 10 and the difference input voltage is 0.5. So that is why we are getting around 5 volt. That is right now we are getting 5.6 because it is input is showing 550 millivolt. Okay, so we are getting 5.5 or 5.6 volt. I mean almost 10 times gain we are getting. Suppose now I am going to change in V2 voltage from 1 volt to 1.5. So obviously, so 1.5 minus from the channel 1.5. Okay, 1.5 minus 0.5. So difference become 1 volt and R2 by R1 is 10. So 1 into 10 is 10. So 10 volt should be at the output. Here you can see this is the input, again reference input, and we are getting the output. If you can see, this is the yellow one. So yellow one is the right now 1.61 it is showing. Okay, and V2 is obviously 0.5 or 0.66 volt. So 1 minus 5 minus 0.5, that means 1 volt, and we are getting around 10.5 volt at the output. So output is the difference of V2 minus V1. Now again we can see this, if I change this 0.5 to 2 volt, 1.5 to 2 volt, now this is 1.5 to 2 volt. Okay, so here you can see we are getting 15 volt because 2 minus 0.5, that will be 1.5. Okay, 1.5 and 1.5 into 10, that is 15 volt. So we are getting 15.1 or 15.3 volt. So here we have seen we can see V2 minus V1 and R2 by R1, that is the gain, that is 10 by 1 kilo ohm. We are getting the gain, and that we are getting the output as a difference of V2 minus V1. So this is the subtractor circuit. Here we can see. So I am going to save the data for the 1 volt. 3 data, I will take 3 data set for the 1 volt right now. So I am going to save it at the USB. So this saving. Okay, now I am going to change it 1.5 volt peak to peak. So here you can see 10 volt or almost we are getting. Again I am going to save, and now again for 2 volt peak to peak. So here you can see, so we are getting around 15. So these 3 data, from these 3 data set we can compare the, and even we can analyze the how this op-amp is behaving like a subtractor circuit of 2 given inputs, V2 and V1. So this is the part for the adder and subtractor circuit. Now another one is another 2 is the left, that is the integrator circuit and the differentiator circuit. So next is integrator circuit. Here you can see in the feedback is capacitor is connected and the input resistance is connected at the input, and we also connected one resistor at the feedback to modify the gain, to improve the gain of the amplifier. So in detail, if you see this circuit, this is the integrator circuit. Here I'll use 1 kilohertz frequency of the input signal. So its time period will be 1 millisecond, and the proper integrator circuit designing this condition, that is T is the time period of the input signal. Okay, and R1 and CF, this is the time constant. This should be much larger than or greater than or equal to time period of the input signal. That define the proper integration actually. So you will get this condition by solving the mathematical part of the voltage of this circuit diagram, input and output voltage. You will get this formula, and this approximation will satisfy this above integration equation. So here I am using 20 nanofarad capacitor as a feedback capacitor, and I will use 100 kilo ohm resistance RF. okay, to adjust the gain, and the input resistance is 10 kilo ohm. Okay, so these are the components. Obviously circuit will be the same. So here you can see circuit is already connected. Okay, so I just connected all the circuits, all the components on the breadboard. Here you can see this is the 10 kilo ohm resistance, and this is the 20 nanofarad capacitor, and this is the 100 kilo ohm resistance. Offset is already connected, nothing is changed, we just connected the R1, okay, and the RF and the CF. The circuit is remained same, but we just removed the older resistance and we connected the this resistance and capacitor according to this circuit diagram, so to design the integrator. So here is the input, which is obviously here you can see the input is giving by through the 10 kilo ohm, and this 10 kilo ohm, and at the output you can see inverted. Okay, here you can see pin number 2, okay, is connected to the capacitor, which is also connected to the 6 number, pin number 6, that is the output, and resistor is also connected. 100 kilo ohm resistor is also connected between 2 to 6, that is inverting input to inverting terminal to output terminal. Okay, these two resistors are also connected. And the third resistance, that is the non-inverting, is this is the non-inverting pin number 3, which is grounded. So the circuit is simple, very simple, and it is connected now. So now I am going to give the supply. I am just going on to give the supply the op amp. So right now it is 15, and the input signal frequency is, here you can see 1 kilohertz. Here you can see 1 kilohertz frequency. Okay, 1 kilohertz frequency, and the amplitude is right now 1 volt peak to peak. Here you can see this is the yellow one is the input. Yellow one input 1.2 or 1 point something 1.3 1.2 or 1.3 volt peak to peak, which is input signal of 1 kilohertz frequency, and right now we are getting output, that is 1.3 volt. Gain is almost same, whatever we are giving, and we are getting the same output with the triangular shape. So if we integrate the square wave, we will get the triangular wave shape, right? Or not triangular, actually this is sawtooth wave shape. Okay, this is triangular actually, no, this is triangular, sorry, not sawtooth. Sawtooth is one is the flat, then other is like slope. So this is triangular. Now come to the another wave shape. Now I am going to apply give a sine wave as an input. So I am giving the sine wave as an input. Here you can see this is a sine wave, and I am getting sine wave as an output. So if you see compare the both the input and the output, so you can see here, sorry, here you can see this is the 0 reference, okay, of the input. Here is the 0, but we are getting maximum. So there is the 90 voltage phase difference between input and the output signal. So obviously if you integrate the sine, we will get the cosine, right? So that is what we are getting. Actually minus or minus, that become actually plus, right? So we are getting plus here, okay, at the output. So this is the sine. Another way, if you use another ramp, if you see the ramp, if you give the ramp as an input, okay, triangular wave as an input, you will get the sine wave actually at the output. Here you can see with obviously same phase difference. So we are getting this. So we will save different output of the different slips, the inputs. So I am going to save it. First, this is the sine wave as an input, and we are getting the cosine wave as an output. Okay, I think there is some problem. Now it is saving. So this one is saved. Another wave form we are also going to save it. Right now it is square wave. Okay. So I am going to save it. it is also saved. Now I am going to give another wave, this one again I'm going to save it. Yes, this is also saved. So this is the integrator. So obviously if we change the frequency, gain will be changed or reactance will be changed, and we will not go on that point. Okay, so the thing is the circuit is designed to integrate the input signal, and we are getting almost the same output gain, okay, for the given capacitor and resistors value. Okay, and this condition and this capacitor and resistor are satisfying the time constant criteria, so for the proper integration of the circuit, and we are getting very good signal, right, integration of the input signal. Okay, so now next is the differentiator. So okay, we'll design the differentiator circuit and we'll see how the input is differentiating at the output. Okay, so you can see the differentiator circuit. This is the differentiator circuit. So if you see clearly here, so this is the clean diagram, clean circuit diagram. So here I have used C1 capacitor as in the input, right, which is obviously same from the previous one, that is 20 nanofarad. I used R1 as a 10 kilo ohm and RF 100 kilo ohm to satisfy the condition for the good differentiator, that is time period of the input signal should be greater than RF and C1 capacitor, time constant of RF and C1. So T should be greater than this. So for that we assumed we have taken 100 Hertz frequency, so it gives us 100 millisecond, and we got the RF 100 kilo ohm and the C1 20 nanofarad, we got out around 2 milliseconds. So the condition is satisfying. So now you can see the circuit. If you see the circuit is connected here, already connected here. So I use this 10 kilo ohm here, and which is connected to the capacitor 20 nanometer, and this capacitor is connected to the inverting terminal, that is pin number 2 of the IC, and from 2 we connected the 100 kilo ohm resistance from 2 to 6 at the output. So this is the RF feedback resistance 100 kilo ohm. This is the C1 capacitor which is connected at the input, and in the series 10 kilo ohm resistance is also connected with the capacitor. So, and the third again non-inverting terminal is grounded. Here you can see this is the pin number 3 which is grounded here, and again this is the remaining 1, 5 and 1, 4 and 5 for the offset, plus 15 for plus 7 and the 4 minus 15, and we are taking out from the pin number 6. Okay, so circuit is connected. So I am going to turn on the power supply. So right now we are giving 15 volt plus minus 15 volt to the op amp. Now I am going to turn on the function generator, that is for the input signal. So right now frequency is 100 Hertz, here you can see, and the amplitude of the signal is 1 volt peak to peak. So I am going to turning on the input signals. Here you can see this. Okay, so this is the input signals and we are getting the output. Okay, so there is the phase difference between input and the output signal. Obviously we are getting the phase difference. So if I compare both the signal, here you can see the close. Obviously we are getting the 90 degree phase difference because we are giving the sine and we are getting the cos. Okay, so inverting is the differentiation part, so we are getting that. Okay, so this is the signal. Now I am going to change the waveform. Let's see what will happen. Before going to change, first I have to save this for the data. So now I'm saving it to the USB. Okay, now I'm going to change the waveform. Now let's select square wave. So for the square wave, we must get the differentiation of the square wave should be spike type signals. as the input is changing from high to low, so it should be, obviously it will take some time, transient time, so it is decreasing very fast. Similarly, from lower to high for the input, again it is going to from minus to 0. So we are getting the some spike top type signal at the output. This is the, obviously this is the, because of the differentiation of the constant, it is almost 0. So in both cases, we should ideally get the straight line, but there is some small finite transition time from high to low or low to high. That is why some king type signals we are getting in the case of square wave. Okay, and now I am going to change ramp wave, that is a triangular. So we have to apply the ramp wave as an input. So we must get the output at the output from the differentiator, obviously square wave. So amplitude is less, so I am going to increase its amplitude almost. So here you can see we are getting the amplitude. Here you can see falling, that is high, from the lower amplitude is increasing. So that is the signal. So we are getting like this. Okay, so almost square we are getting, okay, for the triangular input. So also I am going to save it. So here you can see the circuit is performing very well. It is performing like a good differentiator for the 3 different input signals. We have seen this. So we, according to whatever the signal will give, it will differentiate it, and we will get the differentiation, we will get the accordingly the differentiation. So that is the thing for the, obviously if you talk about the gain are getting almost same, but it is the active filter, active amplifier, active integrator, differentiator and summer. So we can adjust the gain by adjusting the feedback resistance and capacitor, by keeping the condition, time constant condition T for the differentiator, T must be less than RC time constant, and for the integrator obviously T must be greater than or equal to RC time constant. By keeping this condition fixed, we can adjust the gain, and we can get the desired gain of the integrator, differentiator and summer and subtractor. Okay, so these are the things in this experiment, and what you have to do is data will give you the display of this DSO. Here you will find the frequency, amplitude, peak to peak amplitudes of the both input and output signals, and for the different wave shapes. And in the case of adder and subtractor, you will get the 3 to 4 different amplitude, input amplitude, will get the corresponding output gain, okay, output signal. So you just analyze the all 3 signals by comparing their amplitudes peak to peak, and you will see, and you will have to report on the basis of that how much gain you are getting for the different input signals. And here also for the integrator, differentiator, so whatever the signal you are giving after differentiation or integration, whatever you are getting, that is the thing. So in both these two, integrator and differentiator, right now we are not much focusing on the gain, but the thing is how it is, how proper it is converting the signal, I mean differentiating the signal or the integrating the signal. Okay, so that is the thing you have to do on your report, and by getting this data you have to submit your report on time for today. So thank you so much.